Hi, everyone. Welcome to lecture A.5. Today, we're going to switch gears. And rather than talking about, let's say, efficiency benefits of interacting proofs, which is in some sense all we've discussed so far, right? Either for intractable languages or for tractable languages. Either way, it was some efficiency improvement gained by the verifier compared to by itself. Today, we're going to have a lecture about what interactive proofs bring in terms of privacy properties. Okay, and so this brings to the notion of zero-knowledge interactive proofs. So, right. So this notion of zero-knowledge, informally, it means that what we want to do is want to protect the privacy of the prover. So suddenly, our focus, which so far was to primarily protect the verifier, now shifts on the other side. And we want to basically design interactive proofs that do not, in some sense, give away why the statement is true. Okay, of course, the prover shows up to interact with the verifier with the goal to convince the verifier the statement is true. But it could be that you have situations where that's all you want to do. You do not want to also give up why the statement is true. You just want to convince the verifier that it is true. This sounds pretty abstract, but probably a very good way to illustrate this notion is by focusing on the language of graph isomorphism. Okay, it's a language inside NP, which we've seen before. Remember, this is GI, not GNI. So the graph, the language GI consists of pairs of graphs that are isomorphic. And it's an NP, right? Because if I want to prove to you that two graphs are isomorphic, I can just give you the permutation that scrambles the vertices, and you can just go edge by edge and verify that if you take an edge in G0 and you map it into G1 under the permutation, that new pair of vertices is also an edge, and vice versa, right? Moreover, graph isomorphism is, well, first not believed to be NP complete, but it is also not known to be in PPP. In fact, it's almost there, but not quite. It's in quasi-polynomial time. But that is to say that if I am giving you this permutation, in some sense, yes, I'm convincing you that the two graphs are isomorphic, but you're also learning something else, like how they're isomorphic, okay? And giving you the permutation is like a trivial interactive proof, right? Because if you remember, NP is a special case of IP. It is precisely when the prover partakes in interaction in this trivial way by just sending the NP witness. The verifier doesn't flip any coins, just read the NP witness in full and decides whether to accept or reject. Okay, so this trivial interactive proof is an interactive proof. But what if we want to consider the isomorphism? Okay, a private input of the prover that is kind of, the prover knows why the two graphs are isomorphic. Some sort of, you can think about it, some secret key about or some secret proof about why the two graphs are isomorphic. It wants to convince the verifier that they are isomorphic, but is not willing to kind of give any information about this permutation or indeed any other permutation that certifies the isomorphism. Okay. What we're going to see today is how to design an alternative interactive proof for graph isomorphism that is still complete and sound. That's what it means to be an interactive proof. And yet, it will provably reveal information about any isomorphism between G0 and G1. Okay, that is what we're going to do today. So we'll see today's zero-knowledge in this kind of very controlled and illustrative setting. It is, however, hard to give justice to just how enormous of an impact the notion of zero-knowledge has had on cryptography and complexity theory. It originally was born within the context of interactive proofs, precisely through an example such as graph isomorphism, and I guess maybe the original ones for quadratic residuosity. But since then, it has become an absolutely central notion within computer science at large for various reasons. On the one hand, we will see that to define, even to formally mathematically articulate what does it mean for something to be zero knowledge, we're going to work with something known as the simulation paradigm. Okay, this simulation paradigm is a perspective that without it, it would have been really, really difficult to formulate numerous other cryptographic goals that becomes much easier to understand and to formalize if you understand what the simulation paradigm is. Okay, so this was the first known instance of that paradigm, and since then sort of has become like a truly invaluable perspective in cryptography. But also, zero knowledge is a powerful building block where many of sort of foundational feasibility results, such as secure multi-party computation, rely on the existence of zero knowledge. Okay, somehow because we know how to prove things in zero knowledge, therefore we're able to say sort of conduct multi-party computation protocols with this sort of privacy properties, and these things in turn have their own applications beyond zero knowledge standalone, to like secure multi-party computation. So yeah, like zero knowledge is just like this enormous sort of piece of conceptual achievement in theoretical and computer science, and more recently applied cryptography. It's also absolutely beautiful. So I hope you enjoyed. Anyways, that's the plan for today. Any questions at this point? Okay, so off we go. So what we're going to do is, I'm just going to like state.
There are a couple of questions in the chat.
Ah, sorry, I didn't see them. Okay, so let me just go back. So the question is, are there other paradigms for ZK? So the paradigm I was alluding to was not to construct ZK, but was to formulate ZK. Okay, and that is the way that ZK is always defined, through the simulation paradigm. Okay. So in some sense, it is the only paradigm. There are other things that you can talk about, like weaker notions like witness indistinguishability. Those do not go through the simulation paradigm, but it's also not zero knowledge. And does ZK for specific languages imply other cryptographic objects? I'm not what specific languages means, but sort of ZK for various interesting things has its implications. For example, ZK for NP also implies ZK for IP. For instance, that's an example of an implication. And ZK for NP implies sort of all the secure multi-party computation things. So yeah, like there has many applications. We won't see any of them in this course because they're primarily cryptographic in nature. Yeah, hopefully that answers the questions. Yeah. Okay, so what we'll do now is we'll kind of put aside zero knowledge for a moment. We'll see an example of an interactive proof for graph isomorphism, and we'll just argue completeness and soundness, okay? It will be like some odd-looking IP, okay? Because if it wasn't for zero knowledge, we have a perfectly nice IP. It's just send me the permutation, and I'll check it, okay? So this will be some other more kind of convoluted way to prove the same thing, but we'll see later it satisfies zero knowledge, but that's only later. For like in this slide, we'll establish completeness and soundness, which they still have to hold, right? Because it has to be an interactive proof. So here is the interactive proof. Both the prover and the verifier receive as common input the instance that is about which they're discussing. So it's a pair of graphs, G0 and G1. The prover receives as additional auxiliary input this private permutation sigma, okay, that claims to be that it is an isomorphism between G0 and G1. So rather than just literally sending sigma to the verifier, which would have been the trivial interactive proof, what the prover will do, it will instead first pick a random permutation and scramble the first graph without loss of generality. Doesn't really matter whether it's the first one or the second one because they're in the same isomorphism class once they're isomorphic. It gets a scrambled graph, H, and sends it to the verifier, okay? Subsequently, the verifier samples a random bit, sends it to the prover, okay? And the prover sends this permutation, okay? It looks weird, but essentially what the prover is asking is saying, please show me a permutation between the graph GB and the graph you sent me at the very beginning, okay? And if you just look at it here, one way to represent it is exactly this one. Why? Because if B is 0, then the verifier was interested in seeing a permutation between G0 and H. Well, in that case, would have been purely this permutation here, phi. Okay, so it's phi composed with sigma to the 0, that's phi. Okay, so that's great. If instead B had been 1, the verifier would have been interested to see a permutation from G1 to H. Okay, but in that case, because sigma is a permutation, let's say from G0 to G1, it first goes from, sigma should have been from G1 to G0. It goes from G1 to G0, and then you apply phi and you get to H. Okay, so that's exactly what we're going to argue now. Suppose that the two graphs are indeed isomorphic, and suppose that the permutation goes from G1 to G0. Okay, of course, if it goes the other way around, then you can just put a minus sign here and invert the permutation. Whatever bit the verifier definition the check that is performed by a verifier is equivalent to this one by definition of the honest prover, right? Because the honest prover sends psi, which is defined to be this expression, okay? But when you apply sigma to the B, to GB, that's just G0. And so that's as if the verifier would have checked this, but it's exactly how the graph H was constructed. So this is telling us that the verifier always accepts when the verifier is honest and the prover is honest, okay? Are we convinced that this strange looking interactive proof has a perfect completeness? All right, at least one person is convinced. So 2 people, good. Great. Soundness. Suppose that the two graphs are not isomorphic, okay? In this case, whatever the prover sends in the first message, it will be isomorphic to at most one of the two. In fact, if the prover is an idiot, then it will be isomorphic to neither, okay? But in the best case, it will be at most one, right? Because they are in different isomorphism classes. So look, the verifier just samples a random bit, and half the time it will want to see a permutation between one of the graphs and H, and the other half of the time between the other graph and H, okay? So this means that any malicious prover will get caught with probability at least half, okay? There's just no chance they will be able to convince the verifier with more than half the probability, okay? All right, just to summarize, the way this interactive proof works is that in the good case, it just scrambles a graph, sends it, and whichever kind of isomorphism the verifier wants to see, whether from GB or whether from G0 or G1, then the prover always has a way to answer correctly. And in the bad case, whatever the prover sends in the first message, H, it will, in the best case, be able to only show an isomorphism with one of the two graphs, okay? But it doesn't know which one because B is sampled after at random, okay? All right, so look, we have convinced ourselves that this is an interactive proof for graph isomorphism. Any questions about completeness or soundness? Okay, that's a pretty sort of simple protocol, certainly compared to other interactive proofs you've seen the last couple of days. Okay, so now let's go back to trying to define zero knowledge. And the first realization is that if we want to argue that whatever we've seen has some privacy properties, we cannot do it unless we actually stick our neck out and propose a definition, right? Otherwise, what are we going to prove, okay? Or actually, let's go back for a moment. Yeah, like you can see intuitively, okay, we're not sending sigma, so sigma is never sent. Sigma is kind of masked by this phi, but what does that mean? Like, this is just feelings, right? So we cannot just like stare at something and convince and think maybe it is a reasonably private interactive proof. We have to articulate what we mean for something to be zero knowledge. That is a mathematical definition, and against that, definition, we want to try to prove whether it satisfies it. Okay, that's the only way forward. Okay. There's a question about why are we sampling a random permutation? Why not to pick any? Well, that's going to matter. Okay, and more generally, as we'll see, for zero knowledge, it is almost always important for the prover to contribute randomness. Okay, so it will act in random ways that kind of smooth out the information in a way that can be kind of simulated, as we'll see in a moment. Okay, you want to kind of create a distribution that hides information about the particular private input that you have. Okay, so this will come up very soon. All right, so it's actually very important that this permutation phi is sampled at random. All right, so now we kind of put aside, yeah, and here for zero knowledge, we cannot assume without generality that the prover is deterministic, because usually that's done for soundness, right? And for soundness, we don't care what the prover does. Here we do care because it's the honest prover. Yeah. So here is a definition, and we're going to first consider a special case where the verifier acts honestly. We'll come back to the general case later. We're going to say that an interactive proof for a language L is honest verifier zero knowledge. And now is the first time in this course that we encounter the idea of a simulator, and we're going to try to conceptualize what does it mean. If what? Well, we want to compare two things. We want to compare what the verifier learns during a real interaction. Okay, so here's the verifier that shows up and talks to the prover and has a certain view. We'll talk about the view in a moment. Okay, and what we want to say is that whatever things it learned, there is a machine, an efficient machine, probabilistic polynomial time machine that we call the simulator, such that if the claim was true, then the simulator produces the same information. Okay? Crucially, this machine does not have access, for example, to any secret isomorphism. It just only knows the statement, not why the statement is true. It is promised that the statement is true, but nothing else. Okay? So let me just kind of dig deeper. So what is the view? So the view of the verifier in an interaction is, well, it's everything that it sees. So it's randomness. So clearly the verifier uses its own randomness, so it clearly sees its own randomness. The theorem, so the instance, right? And all the messages that it receives from the prover, right? That is everything that happens in an interaction, right? The prover shows up, talks to the prover, and goes away. What has it learned at the end of the day? Well, whatever random coins it had anyways in its pocket, whatever theorem they were talking about, and whatever was received. Do we agree that this is the only things that the verifier knows about, like, and we are interested to discuss, right? So we basically want to try to understand, does this random variable contain any private information coming from the prover? Okay. So before we go back to the definition, are we at least happy with what is a view?
Can I ask a clarifying question?
Yeah.
So when we are writing that left side is equal to the right side, we treat both of them as random variables, right? Where in the left part, the randomness comes from the randomness of the simulator, and in the second part, the randomness comes from the randomness of the prover, right? And then we want that
prover and the verifier. And I'll come back to that in a moment. I moved here for a moment in order to come back to this one in a moment. But yes, what you said is correct. Just the second part is over the randomness of the prover and the verifier. But specifically with respect to the view, are we happy with that? I've left nothing out. This is all the verifier knows in the world. Philip has a question about computational distinguishability. No, right now I'm asking like literally the same random variable. Okay. And again, I'll come back to this. I'll come back to this in a moment. I'm asking right now, are we all happy with what a view means? Okay.
Yeah. Why do we not include the verifiers messages?
It's a great. Okay, that's exactly the question I wanted to elicit. They are determined from these. Okay. Once you give me the randomness from the verifier.
Okay. Yeah.
The input and the message, so they're determined. So I don't need to include them. Okay. Great question. Any other questions about the view?
If there was some like auxiliary information that was available? Like, would that be possible?
It could be possible, and we're not considering now, but it's a great question. Right now, we're considering one interaction, and that's it, okay? But sometimes zero knowledge is defined with auxiliary input, and sometimes zero knowledge is considered in an environment with other zero knowledge protocols. That's like composability questions, and we won't get into it today. It gets messy very quickly. But yes, that is something else that basically you could come in with external information, or you could be like interacting with other protocols at the same time, and those are bringing in information, and you have some sort of, yes, and I'm excluding that. But putting it, let's say that, you know, this is the only interaction that we'll ever have, like in vacuum. This is all the verifier has, okay? Its own randomness, the theorem, and the prover's messages. Its own messages are determined, and this is a random variable, and basically thinking about zero knowledge is equivalent, or at least is the same as thinking about, does this contain any private information, okay? There's a question about what about the verifier's internal state? Again, the internal state can be determined fully from these things, right? From here, you can just run the whole interaction and nothing is unknown, okay? The internal state is the same thing as talking about its messages. It's all determined fully from this. So, and now we come to like the core, like the beautiful idea of zero knowledge. How are we going to articulate that this random variable does not contain any private information? Well, one way to do it is to say, let's take the one public thing out of all of these, the theorem, okay? And give it to a machine, an efficient machine, okay? And ask that machine, without the help of the prover, given that the theorem is true, to just recreate this whole random variable perfectly from scratch, okay? So we're saying an interaction is zero knowledge if the random variable that corresponds from the view after the interaction can be recreated without the help of the prover, just knowing that the theorem is true and knowing the theorem. But no auxiliary, like no information about why the theorem is true, nothing else, okay? And crucially, this machine has to be efficient, right? Because if it was inefficient, you might look for, I don't know, some isomorphism between two graphs and then run the honest prover for the protocol, right? So this has to be something that is like kind of does not have the power of the prover. It just has the power of like a lay person, right? And so, and also it's crucial that we ask the simulator to do this only when we know that the theorem is true. Because remember that the verifier does learn one bit of information by interacting with the prover, and that is that the theorem is true. So we're kind of modding out by that bit when we say that this condition must hold only for x's in L, right? We're saying, yes, you've learned that bit, I'm giving that for you for free, x is in L, done, all right? Beyond that, nothing else. You could have created it yourself. So to create a sample from this distribution, you did not have to go and talk to the prover. You could have stayed home and run the simulator. Okay? So this is like a very precise, and in my opinion, a kind of convincing notion of what sort of lack of private information means. Okay? In some sense, the secret here is the cleverness of this approach is not trying to articulate what is knowledge. That is a really difficult thing to do. Rather, what is lack of knowledge? Okay, lack of knowledge, it is certainly staying home and not talking to anybody and doing things by yourself. Okay, that's what a simulator captures. Okay, right, and so that is the interpretation, and that is what the definition is. It's a clean definition. It's not that complicated. All we're saying is, if you want to show that an interactive proof is Honest-Verifier zero knowledge, all you have to do is give me a candidate simulator and prove this statement. That's it, the end. There's nothing about philosophy. There's just like a simple statement to prove, okay? So, right, and so this is the simulator. And in fact, the simulator like kind of comes up all the time in cryptography. If you want to try to simulate, if you want to try to articulate what is private, what is not private, especially is basically a balance of what to give to the simulator and what to ask the simulator to simulate. Okay, and it's used all over the place in cryptography. This is the first place where it showed up. Notice also that in this Honest-Verifier zero knowledge, like completeness, it is a joint property of the honest prover and the honest verifier. In other words, if the prover is stupid and forgets to run the protocol and just sends this to the verifier the secret input, we can do nothing about it, right? So here we're protecting the honest prover that follows the instructions of the protocol. Similarly, right now, we're still not yet telling the prover that he's protected, even if the verifier deviates from the protocol. We're saying that if the verifier also follows the prescribed instructions, then the prover has this guarantee. Okay, so it's a joint property of the prescribed honest prover and the prescribed honest verifier. Okay, we'll come back to malicious verifier in a moment. We'll just first understand this intermediate notion. Okay, all right, so it's a pretty simple definition. We are about to prove that the previous protocol satisfies this definition. Are there any questions about the definition itself? I hope it makes sense. It's again, it's a beautiful, I don't know, like approach, and the fact that it can even be fulfilled, it's amazing. So it's both like a real, like truly like innovation around definitions, and the fact that they can also be fulfilled by like useful protocols. It's even more surprising. So it's truly like a very special part of computer science. All right, so now we go back to the protocol. Here it is. I've copied up here at the top. Okay, that's the protocol we saw. And our goal now is to prove the claim that this interactive proof satisfies the honest verifier zero knowledge definition from the previous slide. Now, let's fix some instance in the language. And let's try to first clarify to ourselves what is the view of an honest verifier. Okay, because if you want to design a simulator, the simulator is trying to target the honest view. At least clarify to yourself first, what is an honest view looking like, right? Because then it might suggest what the simulator should do. So the honest verifier's view consists of the theorem. Now its randomness, I'm not going to write it separately here because it's just one of the messages anyways. The verifier's entire randomness is just this one message. So I put it here. And then we have the transcript of interaction, where the prover's first message, the verifier's randomness, and the prover's second message. Now, this is a good transcript in the sense that this first message is distributed as a random graph in an isomorphism class. B is a random bit, and psi is random subject to this condition. Okay? Notice that there might be multiple psis that satisfy this condition, right? If the graph has symmetries, maybe there are multiple psis with this one. Okay. Meaning that, you know, once you have fixed H and GB, maybe there are multiple psis that could satisfy the condition. So it will be random given that that is the case. Okay. So this is how like honest view is distributed. And now all we really need to do is to write down a simulator that just given G0 and G1, given that they are isomorphic, will produce a tuple that is so distributed. Okay. Now notice that we cannot, as a simulator, just perform the same operations as the honest prover, because look, if I sample phi and I apply phi to H and I send phi to G0 and I send H, and then I sample B, how on earth am I going to produce psi? Right? To produce psi, I'm going to need information about some sigma, which ties G0 and G1. But even if I am promised that G0 and G1 are isomorphic, as an efficient algorithm, I may not be able to find an isomorphism between them, right? So I cannot just follow the honest prover's kind of protocol, okay? This in general is a hallmark of zero knowledge, right? Like the simulator have to do something slightly different from the honest prover, because otherwise the prover could have just convinced the verifier of these things in the real world, okay? So you need some edge. And the edge we're going to use is the fact that the simulator does not have to reason chronologically. It just needs to produce the right random variable. So it will sample things out of order, okay? So it will sample first B and psi and set H as a function of that, and then output this distribution, okay? And the two tuples are equidistributed because let's see, well, G0 and G1, that's the input that comes in, great. They're isomorphic. So H, is it or is it not a random graph in an isomorphism class of G0? Sure, because look, we picked a random B, then we applied a random permutation, and we applied this random permutation to GB. This whole thing is going to give us something that is equidistributed as if we had sampled phi and applied to G0. It's the same thing, the same random variable, okay? Is B a random bit like it should be? Yeah, it is. We sampled it as a random bit. Is psi random subject to this condition? Yeah, we sampled it, and then we made this condition be true by computing H that way. So this tuple is distributed the same way as this tuple, and that is why the simulator satisfies the condition. All right? Now, in arguing that they're equidistributed, we had to use the fact that G0 and G1 are isomorphic. That's why it's okay to apply psi to GB, okay? We crucially use that. It's not surprising that we have to use that fact, okay? Okay, so that was pretty mechanical in some sense. We just checked what was the honest view, and we designed a simulator for it. Again, no philosophy, no weird musings, just like proving theorems, okay? Even though we're talking about knowledge, right? Or lack thereof. All right, any questions about how this simple interactive proof is honest verifier zero knowledge? Okay, I guess today's lecture is very clear, or at least I hope. Great, so let's move on. Now we're gonna articulate a slightly stronger notion of zero knowledge against malicious verifiers, okay? To do that, we're gonna have to account for verifiers that deviate from the protocol. But once we understood how to do honest verifier zero knowledge, and if we're convinced by that, as a good definition, the step towards malicious verifiers is actually pretty natural. What we're going to do is we're gonna basically say, fix a simulator, and then consider whatever instance in the language and whatever malicious verifier, and just make sure, just remember to give that verifier to the simulator as an input as well, right? Because look, first and foremost, you have to give the code of the malicious verifier to the simulator, because I don't know, if the verifier decides to jump as opposed to, I don't know, lie down, how does the simulator know to do that, right? It needs to know what the malicious verifier would have done in various operations. So we're giving it its chance to know it, right? So its goal now is to basically say, okay, I want to simulate the behavior of the this verifier when it interacts with the prover on this input, okay? And of course, different verifiers may do different things. And so the simulator's strategy will have to depend on the specific verifier it's trying to simulate, whose view it's trying to simulate, okay? Now, a couple of considerations here. First, we're looking at efficient verifiers because, well, the simulator does not have time to run inefficient verifiers. Sounds reasonable. Also, I put here this expectation, which is in some sense unmotivated. Why would you relax your constraint of probabilistic simulators that run in strict polynomial time as opposed to expected polynomial time? Well, it's just because we will have to. It just turns out that if you want to achieve malicious verifier zero knowledge, in many settings, we do not know how to achieve strict polynomial time simulation, and we have evidence that it is not possible. But if we relax it to expected polynomial time simulation, then we can. And it's still a pretty reasonable notion of efficiency. Okay, we're saying that the procedure that simulates the view will terminate in expected polynomial time. Yeah, so that's a pretty reasonable, efficient notion, as opposed to saying will never terminate or it has infinite resources. It's like still something pretty meaningful. Okay, so this is a technical kind of compromise we have to make that comes from specific constructions that we'll see actually in the next slide, that it just naturally comes up. All right, so let me just look at the questions here. All right, so here are various things. People can define malicious verifiers knowledge in a number of ways. Here, I've tried to kind of not make a big deal of the access of the simulator to the verifier and just gave it to it. On most simulation ways that you will see are so-called black boxes. So actually a simulator won't even need to see the code of the verifier, but just run it. Okay, so many times you might see the verifier actually appearing as an oracle, meaning that it has access to the next message functions of the verifier. Another question has to do with the quantification. So another reasonable, weaker notion would have been to say, for every verifier, there is a simulator that simulates things for every X and L, right? There is also a notion that you can consider, and it is meaningful. Just that most of the time, we can actually achieve the stronger notion where you have one simulator that works for every verifier, okay? So these are all variations you might see in the literature. And just as a warning, if you dig into the literature, there's like a million variations of definition. Okay, not like literal million, but they might have more than 10 definitions that will vary in like small technical things. You just need to be able to appreciate what is the specific setting that you might be looking at, okay? And sometimes for technical reasons, you prefer one definition over others, okay? Because some of them are stronger, some of them are more ergonomic, and so on and so forth, right? Okay, so the whole point of malicious verifier, though, is that we're saying that even verifiers that deviate from the protocol cannot learn any information besides the single bit that X is in L, okay? That is what this definition is kind of capturing, saying that the prover does not have to worry about malicious verifiers because they too will be able to be simulated, okay? Now that we have kind of are quantifying over all malicious verifiers, now zero knowledge becomes a property of the honest prover alone, right? The honest prover does not have to trust the verifier to behave, but merely has to ensure that it follows its own instructions. And malicious verifier zero knowledge will make sure that its privacy is protected, okay? So, and here kind of putting the full comparison, completeness is a joint property of the honest prover and the honest verifier. Soundness is a property of the verifier alone, regardless of the prover. Honest verifier knowledge, as we already remarked, is a property of the prover and the verifier. And now we have seen that malicious verifier zero knowledge is a property of the honest prover alone. Okay. Yeah, and here is just the remarks that indeed what was asked. This inexpectation is because of technical reasons. It's still it's a meaningful relaxation that makes it a lot more usable. And other flavors are used. For example, this other quantification, which I kind of laid out here. Okay. And usually what definitions people use have to do with whether they are constructors or users of zero knowledge. If you construct a zero knowledge protocol, typically you define the strongest notion you can achieve, right? If you use a zero knowledge protocol as a building block abstractly, typically you want to try to define the weakest notion that suffices for whatever you want to do, right? That's typically how the preference for definition goes. People that construct want to claim the strongest property. People that are using want to assume the weakest property that they can, right? And that's kind of as a rule of thumb. But sometimes you cannot achieve the strongest notion, and sometimes you cannot build what you want from the weakest notion. And so you may have to do some you may have to discriminate between the different definitions and pick the one that makes sense for you. But here, we wrote one that I find is pretty simple. It is, and we can achieve it in the next slide. Okay. Any further questions about this definition? Again, another beautiful notion. Once you understand Honest-Verifier zero knowledge, the step towards Malicious-Verifier, it's much more kind of manageable. And it's just like the natural thing you would write, if you want to account for malicious verifiers. So, yeah.
Is the expectation over v tilde as well?
Excuse me?
Is the expectation over v tilde and x?
Yeah, it's over everything.
So what if there was like a single v tilde that it always ran in exponential time for?
Well, we're saying polynomial time verifiers.
Yeah, but let's say there's a v tilde that you can only simulate in exponential time. Is that still zero knowledge?
Again, the verifier is bounded to be in strict polynomial time. So whatever you do will always finish in polynomial time on every coin toss.
It might take exponential time to simulate, right?
Excuse me?
But it could take exponential time for the simulator to run.
Okay, so you're asking about the simulator, sorry. Yeah, like the simulator running in expected polynomial time means that there is some chance that it might run in exponential time.
So if that was true for every single input to a particular verifier, like would that not make that verifier bad? It might gain some knowledge.
No, we are fixed. So this is over the simulator. Okay, now I understand. This is over the simulator's coin tosses. Okay, so
okay.
So the simulator has a running time that is a random variable. Okay, so okay, two things. First, the simulator always like hits this view on the nose. Okay, like it is identically distributed. Period. Okay, when the simulator halts, it has sampled the correct distribution. The end. Okay, separately, its running time is a random variable over, of course, its own randomness and its randomness alone, because there's no other randomness here. And when you take the expectation of that random variable, it is a function that is polynomial time of the input x. Okay, that's what it means. It does mean that there might be with some probability, it might run in more than polynomial time. Okay, but this will have to be balanced by some other things so that overall in expectation, it's in polynomial time. Either way, like a Markov argument tells you that there is a good probability it will run, in polynomial time, right? In strict polynomial time.
Okay, thank you very much.
Okay, good questions. Further questions about this? And if this sounds very abstract, again, like in the next slide, you will see an example of such a simulator, and it will have like a very clear distribution of kind of that its running time has a very clear distribution, and it's quite representative of the type of simulators people construct. Okay, so now we go back, and somehow magically, the very same protocol that we already argued was Honest-Verifier zero knowledge is, without change, also Malicious-Verifier zero knowledge. I remark that this is a special property. Typically, if you're designing some complex protocol and you're shooting for Honest-Verifier zero knowledge, you're more likely to just hit that. And if you further want Malicious-Verifier zero knowledge, you may have to do further things to the protocol. Okay, so most protocols don't just auto-satisfy both. Okay, this is just a special property of this cute protocol that happens to satisfy both, and it's very convenient in lecture. So now we're going to take the same protocol and argue that even if the verifier misbehaves, the prover is still protected. So now we're going to fix some pair of isomorphic graphs and some malicious verifier. Okay. Now the malicious verifier view is not distributed the same way as honest verifier's view. It is distributed according to whatever the verifier says. Specifically, first the honest prover sends, as before, a random graph constructed this way. Then b tilde is a bit. Obviously, there's no need to consider situations where the verifier sends a camel, because then the prover would have rejected, and then it's easy to simulate. Okay, so the verifier is supposed to send a bit, let it be a bit. But now it may not be necessarily a random bit. It could be that the bias of this bit is chosen in some complicated way based on the message, the specific message sent by the prover in the first round, right? It could be that the malicious verifier sees this H and picks a bias for its bit, okay? And maybe some other world, had it seen some other graph, it would have picked a different bias, okay? So it could be some potentially really hard to understand bias depending on the bit H, on the graph H. And then, whatever bit is sent, actually here I'm missing a tilde. Let me make a note. Whatever bit is sent, then the prover will reply with H that is, with psi that is mapping from GB tilde to H, right? All right. So that is how a verifier view is distributed. Now, the simulator has this feature that is called, like, we're just going to guess first. So actually, let me take a step back first. I can't go back. So for the simulator, the point is that, look, it might be pretty hard to try to figure out what is this bias, or how does the very malicious verifier reason about deciding how to pick its bit, okay? But here's like a pretty clever strategy. We're still going to pick a bit B at random, and then we're going to see what the verifier does, okay? If we are right, then we were right, okay? And if we picked the wrong bit, we just start the verifier again, and we try again. Anyways, as we'll argue, the verifier won't be able to know which bit we picked. And so we can conclude our attempts in a small number of tries. So let me try to say that precisely. Like before, we're going to pick things out of order. Sample a random bit, then sample the permutation and pick H based on that. Now that we have H, we give the graph H the first message to V tilde, and we see which bit it gives us, some B tilde. If it's different from the one that we had in mind and we were ready for, we just go back to step one and we retry again. Otherwise, we just output it, okay? So this sounds it's pretty daring, but we'll see that it works, and for some very important reasons. First, because the two graphs are isomorphic, H is statistically independent of the bit B. It carries no information about it, okay? So therefore, when we give H to V tilde in some sense wants to try to make our life hard, right? It would truly want to output a bit, B tilde, that is not equal to B, because it will make the life of the simulator harder. But what is it going to do? It receives H, and H carries no information about B. In other words, H is independent of B. So B tilde that is output by V tilde based on H is also independent of B, right? So the probability that they equal is 1/2, and in an expected number of rewinds that is 2, we're going to halt, okay? So I just argued that the simulator runs an expected polynomial time, right? Each of its runs is polynomial time, and in expectation, it takes 2 rewinds to halt, okay? So I'm not saying yet that the simulator outputs the correct distribution. I'm saying that it halts in expected polynomial time because the two graphs are isomorphic.
But this polynomial time is, of course, dependent on the verifier, right? I mean, we can put longer and longer verifiers, and this will be like unbounded.
That's fine, but we have fixed it. We have fixed it, right? It's a polynomial time, right?
So when we say that S runs in polynomial time, this is like a polynomial with respect to some fixed verifier.
Yes, alternatively, you can say it is polynomial in whatever things and the running time of the verifier. Another way to say that.
Thank you.
Yeah, and yet another way to do it is, if you don't literally give the verifier to the simulator, you can put it as an oracle, and then you can factor that away, right? But clearly, right, so putting aside the specifics of the simulator, let's say you take the simplest simulator ever, just run the verifier, right? Let's say the ambiguity you just discussed will continue to exist, right? So you have to somehow resolve it one way or the other by just accounting for it, right? So yeah, different verifiers will have different running times, which if you're charging a simulator for that running time, you have to account for that, right? And a natural way to do it is you just kind of call it a parameter and you say that it's polynomial in that, right? That's one way to do it. All right. So are people convinced that because the two graphs are isomorphic, this simulator runs in expected polynomial time? But there's a question by Val about why can't we just compute H and get B tilde and just output it? Because we need to be ready with psi, right? We cannot just output H and B tilde. We also need to output psi, right? And psi, we would have to output psi relative to GB tilde. But that we wouldn't be able to do because kind of if all I know is H and B tilde, then I have to compute psi kind of with information between G0 and G1, right? And I don't have it. This is the same reason why we picked things out of order in the Honest-Verifier case. Right, I hope that answered Val's question. Like to summarize, the simulator does not know how to answer any B tilde. It only knows how to answer the B from which it computed H from. So that's why, great, okay. Again, it's crucial, right? So the malicious verifier wants to make our life hard, but it can't. H is independent of B. All right, but we're not done. This is just saying that the simulator runs in expected polynomial time. Not only we need that, but we need it to simulate, like to produce the correct distribution. So here, kind of what essentially we're doing is we're doing rejection sampling, okay? And you might fear that by rewinding some number of times, we're biasing the bit, okay? But no, because they're independent. So one simple way you can argue it is to say, well, look, what is the bias of the bit we ultimately output given that it equals the bit B? Okay, because that's when we output things. Well, by kind of, what is this thing called? Has a name, this quality. I guess law condition, the Bayes rule, thank you. By Bayes rule, I can rewrite this conditional probability as the end of these two events divided by the probability that they equal, okay? But because, B is independent of B tilde, the probability that they equal is exactly half. And the probability that B equals to B tilde is again exactly half, right? So I can just write it like this way. And this is saying that the probability that B tilde equals 0, given that equals B, is the same that it equals 0 to begin with, okay? And this maybe is intuitively clear. This may or may not have helped, but it's the way to kind of formalize that we're doing rejection sampling, okay? That we're not biasing it because we're rejecting based on an independent random variable, okay? And so whenever we do output, kind of the output kind of has the same bias, has the same distribution. Okay, an analogy would be, I don't know, say that you want to sample, there's this nice sort of analogies from sampling from interesting distributions, like say you want to sample a random variable from a circle, okay? One way you can do it is you can sample a random variable from the square around it and just reject if you're outside of the circle, okay? This is like, for example, used for sampling something like in a circle, which could be awkward to do it directly using a computer program, okay? And because whether you're inside the circle or outside the circle is independent of kind of what is the distribution of the circle, then kind of the conditional distribution is still uniform in the circle, right? So it's kind of rejection sampling is that very same concept. So is there a Bayes step in the redundant? We still need to argue that one way or the other, with or without Bayes, we need to argue this is the case. We can, maybe there's other ways to argue it, but we need to argue it, right? We need to argue that ultimately the bias of B tilde is the one that V tilde would have chosen in one execution, okay? So there may be other derivations. I might get confused to try to do it on the fly, but one way or the other, we need to argue that B tilde has the correct bias based on H, okay? So I'm not gonna try to do a different derivation here. If you have a different derivation in mind, maybe we can do it after lecture. Any further questions about another point here is that notice that the verifier, we did not use its code. All we cared about was its input-output relationship. Given H, what B tilde you give me? The end. Okay, I did not care about how you compute B tilde from H. Almost all, though not all, zero-knowledge proofs are of this character. Some of them actually use the code, and they're pretty advanced and complicated constructions. Is it possible to get a simulator that still runs in strict polynomial time, produces the exact view? In this case, no. And there are basically lower bounds that tell us that if you wanted a simulator to run in a strict polynomial time against malicious verifiers, then your language, cannot be too hard. Okay, and there are sort of theorems in cryptography that tell you kind of what happens there. But in general, let's say for interactive proofs and interesting languages, you generally expect an expected polynomial time simulator. But in other settings, you don't. And I'll actually point out a setting maybe like in one or two slides.
I have a question regarding using the verifier in a white box manner. So how should this be possible? Because the simulator in our the way we define it, the simulator should be able to simulate for all verifiers. So this sounds really complicated, and somehow the simulator would need to parse the algorithm, and depending on what's in, so you cannot define in advance.
Wait, hold on, I don't understand. So here we're just running the simulator. I mean, the verifier is a subroutine. What's complicated about it?
Yep. How would white box simulation work? Because the verifier does not know that the simulator gets the verifier as an input, so he would need to parse his code and. Yeah,
but we can. I mean, we have computers, right? So you can read code and you can run it.
But yeah, I just can't see. Yeah, it seems tricky. But okay, never mind. Thank you.
Look, in general, I can represent a program as data, right, and parse that data into a program and run it, right? That's how simulate. Like, forget zero-knowledge simulator. I mean, an actual simulator, right? If you're running, I don't know, like a cell phone simulator inside a computer, right? That is what's happening, right? You have some representation of some Android system, and you just run it inside the computer, even though it's not literally like an Android, right? So similarly here, like you have the description of a program, right? I just look at it and I start running it, and I just keep track of its program counter. I keep track of maybe its tapes, and sort of I myself as a universal machine, like. Of course, you're going to need like some universal simulator underneath. And again, simulator is an overloaded word in English right now. I'm talking about like simulating the computation of other programs. But in general, like sort of, okay, we're not discussing models of computation in this course, but it is like a rather standard thing to tell a program, hey, here's a program, please run it as a subroutine. It's like normal, right? And the simulator certainly can simulate. This is a terrible word. Maybe I should use emulate. It runs the verifier by emulating its computation one step at a time, right?
Okay, but first you try to write a simulator that uses the verifier in a black box manner, and if you can't do that, then you do this crazy thing and try to look at his code. It's just the order of things. So first you try the black box approach, which seems to be easier, and then.
Okay, maybe I thought your question was about something else. I'm not trying to suggest what happens in a zero-knowledge proof where you must use the code. Whatever happens is magical, and we're not going to discuss it. Okay, so but in, let's say, I really mean, like it's pretty complicated what happens there. So and you do need the code, but it's actually connected to probabilistic proofs in some roundabout way, but we won't get into it now. But for normal ones, you're just running it as a subroutine. Like, so do we agree that this simulator, it is legit to receive a program and run it as a subroutine? You can think of it as a black box, right? Or not, right? Certainly, if you are happy as a simulator with a black box, you can only be happier if I give you the code, right? Because given the code, you can just run it, right? You can do more things, but this particular simulator is completely uninterested in those other things you can do. It doesn't need them, right? And, sorry, I thought your first question I thought was specifically about this, but you were asking about what happens in other settings. And whatever happens in other settings is just not this, it's just other stuff. I mean, to give an inkling of what happens in those other settings, the reason why you need the code is because in certain zero-knowledge proofs, you want to write a theorem about the verifier and prove it. And in order to do it, you cannot have it as a black box. You have to actually open it up and look at what it is and like parse it as gates, as some program, and then you prove a theorem about the verifier, okay? So this is roughly the way that sort of non-black box zero-knowledge operates, is you have subroutines that require proving statements about the malicious verifier's code. And because of that, yeah, but it's not like you look at the code and try to understand what's going on. You just parse it for the purpose of proving things about it, using probabilistic proofs, actually. So kind of like these constructions of PCPs and IOPs and whatever, they kind of come back as cryptographic proofs that you can then use to construct zero-knowledge proofs with non-black box simulation. It's kind of a pretty roundabout way that come back here. The question by Philip is saying, like, is it the case that, if you achieve zero-knowledge in a black box way, is it stronger than non-black box? Yeah, because we are kind of tying the hands of the simulator in some way. We're saying, look, you must simulate, but you cannot look at the code. You can only use the input-output relationship of the function. So this can only be a stronger property. And it is. Like, there are settings where you do want to use black box simulation because it has some extra, composability properties that are like nicer to use than if you didn't have that. Okay. Good questions. Any further questions about this? As far as I know, this is like perhaps the simplest illustration of a non-trivial zero-knowledge proof with malicious verifier. It's a very clean setting where to see many of the features that appear in much more complicated proofs. Now, a couple of points about honest verifier versus malicious verifier. You might ask, wait a second, like, who cares about honest verifier? Like, if I couldn't trust the verifier to learn information, if I couldn't trust the verifier to share private information to begin with, how could I trust them to not misbehave if there's an opportunity to learn private information, right? Yeah, like, look, fair point. But there's like two answers to that. One is that honest verifier zero-knowledge actually is a complexity class of its own with nice properties, and people study it kind of regardless of applications. Oh, that's a bit of a silly answer, maybe more of an answer for a complexity theorist, okay? But the other answer is that there are cryptographic compilation methods where kind of the malicious verifier will come for free after compilation. And the canonical example is the Fiat-Shamir transformation, which is not subject of this school, but some of you may have heard it. And it is a way to take an interactive proof, turn it into a non-interactive proof. And it has the property that if the thing that you started from was honest verifier zero knowledge, then after compilation, it is malicious verifier zero knowledge for free. Okay? So there are settings where even though ultimately we both agree that malicious verifier zero knowledge is what we want, merely achieving honest verifier zero knowledge as a stepping stone is a useful goal. Okay? So because of both of these reasons, honest verifier zero knowledge plays an important role nonetheless throughout cryptography and complexity theory. All right. So, okay, great. So we've seen one example, proved both properties about it, honest verifier and malicious verifier. But it turns out that for interactive proofs, there aren't many good news about zero knowledge. Because look, we kind of started out talking about interactive proofs, and we gave this example to GNI, and then we say, oh, GNI is kind of uninteresting. What about CoNP, sharp-sat, p-space? Went very far, right? Here we could say, okay, we did it for GI. How about NP, right? It would be nice to have zero knowledge for all of NP for languages that are actually more interesting. So here you could define these complexity classes to be all languages that have interactive proofs with Honest-Verifier zero knowledge and Malicious-Verifier zero knowledge, right? And it's pretty easy to see that whatever these classes are, there's like trivial inclusions that if I add Honest-Verifier zero knowledge, I cannot get a larger set. At best, it's like a subset. And ditto, if I sort of put Malicious-Verifier zero knowledge, it's an additional requirement, so I'll get an even smaller, potentially smaller set, right? But the question is, how do they really compare? Like, we know that IP is enormous, right? We already proved that this is p-space, okay? On the other side, we know that zero knowledge is kind of for free for BPP, right? Because the simulator can just run the BPP algorithm and that's it. There's nothing to simulate, okay? And we know that kind of there is something non-trivial about the hardest class that we put GI in it, right? So you can ask what other languages have zero knowledge interactive proofs, either Malicious-Verifier or Honest-Verifier. And there's a piece of bad news that one can prove that the bigger of the two classes, Honest-Verifier zero knowledge, must be contained in the intersection of something called AM and CO-AM. Now, we did not cover in this course what is AM and CO-AM. Roughly speaking, these are, you can think about it as one round interactive proofs. Like AM is like one round interactive proofs with public coins. Okay, so back and forth. Okay, and CO-AM is the complement of that. And for reasons that, again, have to do with complexity theory that we're not going to get into this course, anything that is inside this intersection is not expected to be NP complete. Therefore, we do not expect NP to have even Honest-Verifier zero knowledge interactive proofs, which is pretty annoying. And this is true even if we relax the requirement of the simulator to require that the simulated view and the real view are statistically close rather than equal. Okay? As opposed to perfect simulation, statistical simulation. Okay? So again, I'm not talking about this theory. I will say a little bit about this later, like as a high-level intuition. But the point being is that kind of whatever is inside this intersection is not NP complete. Okay? This is not believed to be NP complete because if it were, then weird things happen in complexity theory. And so that's a problem. But on the flip side, kind of you must have heard that zero knowledge proofs are so useful. They can be used for all kinds of statements, including NP. So what gives? Okay. The point is that there are ways to overcome these limitations, and there's generally two types of ways you can overcome them. Okay. One is we can relax this requirement of the simulator further to merely ask that this random variable and this random variable are computationally close rather than statistically close. Now, we are not going to talk about in this class about cryptographic notions. Computational indistinguishability is a cryptographic notion, but roughly speaking, it basically says, I'm only going to ask that this random variable and this random variable cannot be distinguished by any efficient procedure. They may have large statistical distance, but efficient procedures will not be able to tell whether a sample comes from here or from here. So this leads to notions of Honest-Verifier computational zero knowledge and Malicious-Verifier computational zero knowledge. And for these classes, you can show that all of IP has zero knowledge under a pretty minimal assumption, something known as one-way functions. Okay. But anyway, this slide is a bit of an overview. I'm not saying like super precise things relative to the background of this course. I'm primarily kind of putting things in context. So one way to overcome the limitation is to say, okay, let's relax the simulation guarantee. And under some pretty minimal cryptographic assumptions, you can prove that any language that has an interactive proof has a Malicious-Verifier computational zero knowledge interactive proof, including NP, by the way, right? Because NP is included, and in fact, IP as well. This is it's a beautiful and sort of foundational result in cryptography. you know, if you have cryptographic background, I encourage you to kind of look it up and learn about it. It's a pretty kind of nice and elegant proof. But you know, this definitely is a way to overcome the limitation. There's an alternative way, which is to change the model. Okay, you just say, look, okay, I don't want to talk about interactive proofs. Let's talk about something else. Okay, and in fact, actually, in this course, we do talk about other interactive proofs as well, right? There's like IOPs, there's PCPs, I mean, other types of probabilistic proofs, and all of them, zero knowledge behaves a little bit differently in each one of them. Okay, it just so happens in interactive proofs is particularly limited. Right, so that's what I just said. I'll just mention perhaps the most well-known example of a way to circumvent zero knowledge, and that has to do with multi-prover interactive proofs. So you can define the notion of multi-prover interactive proof to be basically an interactive proof where you talk to two or more provers that cannot communicate. And with this multiple prover notion, you can prove that everything that has an MIP, this multi-prover interactive proof, has a perfect zero knowledge multi-prover interactive proof. In this case, in some sense, you can view the cryptography as being replaced by a physical assumption, the fact that these two provers cannot communicate. Okay, and built out of this assumption, you can essentially recreate something analogous to that in an information theoretic world. Earlier, there was a question about strict simulation versus expected simulation. This is an example of a setting where simulation is perfect and is strict polynomial time. So there is no need in the setting to have expected polynomial time simulation. There's another foundational paper. In fact, the paper that introduced multi-prover interactive proofs in 1988 was not about whatever other things multi-prover interactive proofs became famous for eventually. For example, hardness of approximation or quantum, so like MIP star. It was actually about zero knowledge. The paper that introduced it was precisely saying, let's study how we can achieve zero knowledge without cryptography. Okay, and in order to do that, they formulated this notion of multiple provers. Okay, so, and the reason why I mentioned these is that kind of these are like the two ways in which it's helpful to remind yourself that how can you overcome barriers computationally or by just changing the model within your working. And for zero knowledge, both of these lead to very powerful results of feasibility for zero knowledge. Okay. Okay. Now, again, we will not be seeing any of these theorems, but I'm telling you like they exist and you know how they related to the things that we see. Any questions high level about what we've discussed?
Maybe just again high level. I was actually curious about how is it possible that limiting the prover power, like essentially having multiple provers that cannot communicate, allow you to achieve like zero knowledge, which is a property that should actually limit the verifier power essentially. So, if there is any high level intuition about.
Yeah, it's a complex answer because it's not even necessarily about zero knowledge. It's, for example, MIP equals NEXP. So, which is more than P space. So, in fact, by making the prover slightly less powerful, okay, the verifier gained more power to be convinced of more languages. So the point is that it is kind of how to say. It is somewhat incomparable in the sense that kind of in the case of an interactive proof, yes, you had the help of the prover, but it was maybe too strong of a prover, okay? Like you had the option to hang around and talk to the prover, but you did not have the option of spot checking the prover by asking like related questions to different provers, right? So you did gain some power, but the prover was kind of too strong, okay? There are types of questions you can ask with multiple provers that you just cannot ask to one prover. And that is, you produce two correlated questions, you provide them to both provers, and each of the provers doesn't know the full extent of the other question, right? And this is like similar to when you try to gain this, the kind of human analogy that is usually made for MIP is that when you have, two criminals and you kind of put them in separate rooms and they have a prior strategy, of course. They have agreed in advance some story, when you start digging independently in separate rooms, you will have an easier chance at learning the truth. And of course, you're better off that they are there than they hadn't been there altogether, right? So if there is no criminals to interrogate, you will certainly learn no information. So it is better to have the criminals around, but it's actually better to have them in separate rooms than together in the same room. Okay.
See, and also I guess that this is also why, I mean, you can achieve like perfect zero knowledge. Like you have weaker prover, but the simulator has more power instead of the prover to actually simulate the transcript in a way. Yeah, the simulator has a more power in what it can do, and this power is explicitly used indeed in the MIP. Yeah. So, but these are only, like, in some sense, kind of intuitive things, right? It could have been that we live in a world where, whether you separate the provers or not, somehow through some magical arithmetization trick, it doesn't matter in the end, right? Because just these human intuitions are only go so far, right? But good question. All right, so further, but yeah, like I'm really not giving justice to these things. Both of these are, if I had to do like a top 5 list of the results ever proved in cryptography, like these would probably, at least one of these would be in the top 5. Certainly both of them in the top 10. They're absolutely landmark results. So for those of you with cryptographic interests, definitely encourage you to kind of look at them. It's a good question about, so, okay, but, overcome this, overcome that, what's actually deployed in the real world, right? So in the real world, it's something even more different than that. So there's a third option, which is you can consider a setting where the way you help the simulator is you have a setup, like some kind of some public string that everybody trusts has been produced correctly, maybe some randomness or some structured string in the sky. This is called like a common reference string, okay? CRS, yes. And in that world, what is deployed is something that is perfect zero knowledge, but not statistically sound. It is computationally sound, okay? And we have good reasons to understand why it must be computationally sound and why it is perfect zero knowledge. So, so yeah, there's yet other ways to overcome these things. What is deployed in the real world are all non-interactive things that rely on a setup, whether it is just random or something more complicated than random. It's kind of beyond the point right now, and they're all pretty much all perfect zero knowledge with computational soundness. And yeah, maybe there will be someday like a top 10 school, but for now, this is the one we have. Yeah, this is not the school that you want, but this is the school that you need. This is the one that you need first, some foundations. Sort of maybe bad reference to the Dark Knight trilogy. Anyways, the onwards. So now let's go back to the limitations on Honest-Verifier zero knowledge interactive proofs. Okay, like why on earth could it be that having a simulator is a bad thing? Okay, so I'm just gonna give like some high-level intuition that we're gonna be done. So we're gonna see like some super high-level intuition for why, if you give me a language that has, an Honest-Verifier interactive proof, then you can prove its complement without zero knowledge, basically with the same number of rounds. So intuitively, you want to you have to use the simulator somewhere, okay? Because that's what being zero knowledge means. And we know that the simulator, when the instance is in the language, it will simulate the right thing. Okay, that's kind of what it says. But now we can ask, so what does the simulator do if we run it on an instance that is not in the language? Okay, I mean, it's a machine, I can do it, right? Like it cannot refuse to do it, right? We can just press play on an input that is not in the language and see what happens, right? Now, look, at various things could happen. Maybe the simulator explodes, right? That's one option. Like it outputs some garbage or it just does something totally weird, right? Maybe it will output something, a view that like looks legit, is just rejecting, right?
like it has all the tuples, but when you run the verifier on it, it's just a rejecting view. Okay. Another option is that it could be outputting an accepting view. Okay. Now, if we were in the case of 1 and 2, if the simulator does something completely egregious that is easy to detect, we don't expect this to really happen for interesting languages, because if so, if the simulator when X is not in L does something egregious, then we have a BPP algorithm for things. If X is in L, the simulator does not do something egregious. If X is not in L, then the simulator does do something egregious. The end, we can just decide the language, it's in BPP. So really, for interesting languages, most simulators we construct are going to fall into the third case, where the simulator does produce something that is accepting, but there's something off about it, okay? And what's off is that the distribution of the tuple, it must be in some sense statistically far from the real distribution, because the real distribution would have been rejecting by the soundness condition, okay? So when X is in L, you have the real view that is a rejecting transcript and the simulated view, which is an accepting transcript. So they must be statistically far, okay? And so at a very high level, what you can do is you design a verifier for the complement of the language, where you ask the prover to help you prove that whatever is sampled by the simulator is far from a real view, okay? And now, in 5 minutes, I'm going to tie this back to GI and show a connection between GI and GNI precisely because of this. Okay, I'm not talking about the general protocol, but I'm just showing what's a feature. So the fact that we have a zero-knowledge proof for GI is the same reason for why we have an interactive proof for GNI. Why? So consider the zero-knowledge interactive proof for GI that we have seen, and its zero-knowledge simulator. So here is the proof for GI, and here's its simulator. Let's say the honest one, because it's enough. We've seen what happens when the two graphs are isomorphic, right? It produces the right view. But if the two graphs are not isomorphic, this one will still produce an accepting view, but with a different distribution. And we can actually use this to recover the protocol for GNI as a consequence of the fact that the simulator exists. If you remember, the protocol for GNI was something like this. This is the first interactive proof we've seen in the first lecture. It was basically saying, sample a random bit and scramble one of the two graphs at random and ask the prover, which graph do I have in mind? Because he was trying to convince me that the two graphs are not isomorphic. But if you see this thing here, this is like code directly from the simulator. And the bit B can be interpreted as the prover trying to convince me, hey, I know we are in the GNI case. The two distributions are far. Let me prove that to you. I know B tilde all the time, right? So you can actually view the GNI proof that we've seen at the beginning of the whole school as a side effect of the Honest-Verifier simulator for GI, okay? And this is an example of a general paradigm. Like whenever you have a simulator, okay, you can basically leverage the fact that it exists by asking the prover to help you prove to you the complement of the language, okay? And this is pretty, I don't know, like a super kind of, I don't know, like a roundabout connection. And this is why, in the specific case of interactive proofs, we cannot expect such strong things. It's, roughly speaking, whenever you can prove a language and its complement in the same number of rounds, roughly, that means that you can compress number of rounds as well. And these are like other things that we're not discussing, but you can really see this phenomenon that connects zero knowledge for GI to something not zero knowledge for its complement, GNI. Okay, and kind of this is kind of directly from the simulator up here. Okay, it is basically the verifier is running the simulator for the GI proof. All right, and yeah, so this is what happens, and these things are covered in a little bit more detail in the lecture notes, the written ones. And you know, if you have like, if you're interested to look into it more carefully, then you can sort of look there. I don't know if some of you have been looking in the lecture notes, but you know, they are there with a few more details. I think now is a good time for me to stop, and I'll take more questions. Oh, I wasn't stopping, I was stopped the recording.